Hello and welcome to the lab, Heat and Temperature. In this lab, we will be using a resistor to raise the temperature of water and a digital thermometer to look at the behavior between the amount of applied heat and the change in temperature. So, in this video, I'm going to show you the parts that are required to do the experiment. We have our data acquisition system over here. We have a power amplifier, which is going to supply energy to the resistor. This is the resistor right here that's going to heat the water up. We have a thermometer, which will hook to the data acquisition unit, and this is an adapter right here to allow it to do so. We have an insulated container for the water. The instructions that you get say to use a 100 milliliter graduated cylinder. I tried to avoid glass in the lab, so I have a syringe that will go up to 100 millimeters to put water in. Now, in the next video, I'm going to show you the experiment set up, and then we'll do a trial run. This is the experiment as set up. As you can see, the power amplifier connects to the data acquisition unit, which we'll use to actually adjust the amount of energy that goes into the water, which is inside the container, through the resistor. The resistor itself sits on a lip that's been sort of divoted on the side of our container right here to allow the cables to pass. This actually would sit flat, if there wasn't a bend to it. I'm going to take the bend out when we do a run. As you can see, we also have the thermometer hooked up for data acquisition right here, and that goes into the water as well. Now in the next video, I'm going to show you an example of a trial run just to give you an idea of how it works. There's really not a whole lot to see since everything is taken via the computer screen and there's nothing really mechanical going on. But I'll talk a little bit about how the experiment is run in that video. So in this video, we're going to talk a little bit about what you're going to do in the lab. So I wanted to show you the syringe here. As you can see, the syringe actually measures up to 60 cc's, that's cubic centimeters. 1 cubic centimeter is the same as 1 milliliter. So basically what you'll do is you're going to do two runs. The first run has 100 milliliters of water, and the second run has 200 milliliters of water. So for the first run, you would use 2 syringes worth, measuring to 50 cc's, and then in the second run, you would use 4 of them measuring to 50 cc's. You have a total of 20 milliliters. Now, the recording mechanism actually starts at 20 degrees Celsius. So depending upon the temperature of the tap water, either you're going to immediately have it start recording, or the thermal resistor will raise the temperature up to the point to when it starts to record. So you start your experiment first, and like I said initially, with 100 milliliters. What happens is the thermal resistor here starts to heat the water. Once it hits 20 degrees Celsius, that's when this starts to actually acquire data. And it acquires data for about 20 minutes. So you'll do one run of this, looking at the relationship between the amount of heat that's being applied, which is actually measured because we know the properties of the power output of the resistor here. And you'll look at that in comparison to the change in temperature. And then you're going to do exactly the same thing. You'll dump the water out, you'll put fresh water in, and you'll do exactly the same thing for the 200 milliliters. So 2 total runs. The apparatus is set up to take 1 sample every second, because it takes a while for water to go up. And while you're doing that, what you're going to want to do with the thermometer here is to agitate the water a little bit. So if you were to look inside here, and I don't have any water here, so you can actually see what's going on in here. As you can see, the thermistor sits in there in only one place. So the water around it is going to be heated up the most, and then that heat's going to gradually sort of transport itself into the remaining water in there. So what you're going to want to do as you heat it up is to sort of agitate like this during the heating process. And what that does is to help stir the water up and hopefully keep sort of a uniform temperature in the styrofoam cup as it increases. So the temperature sort of increases uniformly as well. So you don't have any weird spikes, you know, if the thermometer were to reach over and bump the thermistor or something like that. So like I said, 2 runs, one with 100 milliliters of water and one with 200 milliliters of water. Hello and welcome to the theory section for the lab heat and temperature. In this lab, you're placing a sample of water in an insulated container and putting a resistor that provides heating to that sample of water, and also a temperature sensor. So what I'd like to look at in the theory section just briefly is what the expected sort of outcome is. Now, your resistor is something that provides power. You know, we know power is energy over time. So the idea here is you place your resistor in water, you allow it to do its job, and over time you should apply a set amount of total heat. So if you think about specific heats, we know that when you heat something, dependent upon what its specific heat is and how much of it you have, you're going to see a corresponding change of temperature, presuming that you're not heating during a change of state. So what happens is for about 10 minutes, which is 600 seconds, this resistor is at work, so it's doing its thing. So what you end up with is having a total amount of heat being dumped by the resistor into the water that would be equal to the power of the resistor and how much time the resistor has been submerged. So this right here is going to be the heat that is going to be responsible for causing the change of temperature that you see. So if you were to put this into this equation over here, P times delta T would equal to C times M times delta big T, which is your change in temperature. Now, as you plot the temperature versus time, and let me just go ahead and make a little axis here, a little graph. Okay. Now, it's not designed to turn on and start recording until about 20 degrees Celsius. Okay. So if you think of this as time axis right here, and this right here is the big T, the temperature axis, then what you should see is, because here time is proportional to the change in temperature. Okay, so time is proportional to your change in temperature. Why is it proportional? Well, the power output of the resistor is constant. The specific heat of your water, which is 4186 joules, per per kilogram per degree Celsius. This is constant right here, and along with your mass. Your mass you can get, by looking at how much water you have. So this right here is constant. This is constant right here. So what you have here is, if you think of a line, is basically T. I'm going to drop the delta for a moment. Is equal to some constant, which I'll call cursive K, times the temperature. So what you expect here, since this is positive and this is positive, is you expect a positive slope here, at least as drawn. And it's going to look something like this. Actually, let me be a little more pedantic about this. Since it starts at 20 Celsius, we'll do it like that. Okay. So you should see, when you plot this, a temperature that changes correspondingly over time. Now that said, you're using 2 different samples of water. If I remember correctly, one is 100 milliliters and another is 200 milliliters. So as you can see, if you were to look at what the value of the slope is here, which is Cm over P, as you can see here, with a bigger mass, you have a bigger slope. So what you're going to see here is, because you're plotting the inverse Okay, since this is the temperature axis is on Y and the time axis is on X, what you're going to see is a slope that looks something like this. So you should see when you plot this a slope something like this for the 200 milliliter sample and a slope something like this for the 100 milliliter sample. Now, so that's about it, just to sort of explain what's going on with respect to the theory. And I'll see you in the lab.